It's Paul here to teach you about row reduction. You should have read through the first two subsections of Module 1, Week 3, because what I'm going to teach you is the details of the algorithm that's described there. Let's start out with a really simple example. We've got a pair of equations in two unknowns, 2x plus 2y equals 8, x plus 4y equals 7, and we will put these into matrix form by converting the coefficients 2, 2, and 8 in the top row into a vector, and the coefficients 0, 4, and the constant 7 from the bottom row into a second vector. We will bind those into a matrix. So you can see what's happened. I've just rewritten the equations without the x, the y, and the equal sign. Now think how you do these using elementary algebra. The obvious first step is to divide the first equation by 2, converting it into x plus y equals 4. And I can do that in R by dividing row R1 by 2. I display the result as a guide to what I should do next. I now realize that if I subtract the top row from the second row, I will convert the second row into something that corresponds to an equation that doesn't involve x at all. So I replace R2 by R2 minus R1, and the bottom equation now corresponds to 3y equals 3. That pretty close to tells me what y is. All I have to do is divide that second row by 3, and now the second equation says that y is equal to 1, and knowing that, I realize that if I subtract the bottom row from the top row, I will get a top row that's an equation involving nothing but x. At this point, what I've done is to convert the top row into the equation x equals 3, the bottom row into the equation y equals 1, and I've solved the two equations. No matter how many equations you've got and how many unknowns you've got, this is the basic approach. The computation gets messier and messier as you get more and more equations, but if you're doing it on a computer, that doesn't make any difference. Now, in this particular case, you know a quicker way to solve the equation. I can make a matrix from the left-hand side of my original equation, the vector 8, 7 from the right-hand side, and when I call the solve function, it says, yeah, the solution is x equals 3, y equals 1. But solve doesn't always work. Here's an example where solve fails for an obvious reason. Here's a pair of equations. Well, they're not really a pair of equations because they're both equivalent to x plus 2y equals 7, aren't they? How would we discover that? Again, we convert the coefficients into two rows, which we then bind into a matrix. Having made the matrix, we try solve with the vector w on the right, the matrix A on the left, and all we get is an error message. The system is exactly singular. What happens if we do it by row reduction? Well, the first step's the same. We divide the top row by 2 to convert the first equation into x plus 2y equals 7. We then subtract the first row from the second row, and the second row says 0 times x plus 0 times y equals 0, which is true, but which provides absolutely no information that will help us to determine x and y. We really, in effect, have only one equation here. That doesn't mean there are no solutions, though. What it means is that we can choose any value we like for y, and having chosen that value, we know that x has to equal 7 minus 2 times y. So we have, in fact, found not only one, but many solutions to the equation that solve reviews to solve for us. If I set y equal to 2, then when I calculate x, it turns out to have the value 7 minus 4, or 3. When I make xy into a vector and plug it in, it works. If I set y equal to minus 1, then my equation, which is x plus 2y equals 7 says x minus 2 equals 7. X in this case has to equal 9, but again, the vector made from x and y solves the equation. As you almost certainly recall from your first algebra course, there's a third possibility. There may be no solution at all. Here's a minor variation on the previous example where I have made the second equation inconsistent with the first equation. There are no values of x and y that solve this pair of equations. How would we discover this by row reduction? Easy. Again, make the two equations into vectors, bind those together as rows to get our matrix. Row reduce, same first step, divide the top row by 2. Now what we have to do is subtract 3 times the top row from the bottom row, and we look at the bottom row. What does it mean? 0 times x plus 0 times y equals 3. There's no solution to that. 0 times x plus 0 times y is always 0, so we reluctantly conclude this system of equations has no solution. Now let's go to what was probably the messiest case you dealt with in your first linear algebra course, namely 3 equations and 3 unknowns. So there's 3 equations and 3 unknowns, x, y, and z. Exactly the same process will work. From 2x plus 3y minus z equals 4, I make the vector 2, 3, minus 1, 4. I do the same with the other 2 equations. Each of these then becomes a row of a matrix. So there's the matrix made from this system of equations. Now I'll be a little bit more systematic about the row reduction algorithm. I see that as the rows stand, I can convert the upper left-hand entry, the first non-zero entry in the top row, into a pivotal 1. I do that by dividing by 2 that entry. Now I have my pivotal 1 at the top of the left-hand column. I have to make that column into a pivotal column, and the way I do that is by subtracting 3 times the entire top row from the second row, 1 times the entire top row from the third row. Because R happily deals with each row as a vector, it's very easy to write these instructions down. And now you can see I've successfully created a pivotal column, the first column. Now let's try to do the same thing with column 2. The first non-zero entry is the second one, minus 5.5, so I divide by minus 5.5. And now you see why this can get a bit unpleasant when you're doing it by hand. You're dividing by first entries, and in general, unless the numbers have been carefully rigged by your instructor, that's going to introduce fractions. As you keep doing this, you'll get fractions with larger and larger denominators, and you'll get more and more distasteful arithmetic problems to solve. But R doesn't care about that. It converts that second entry to a 1. And now you see what we have to do next. Subtract 1.5 times R2 from R1. Subtract 0.5 times R2 from R3. And we've converted the second column into a pivotal column. For the third column, I have to divide by the bottom entry. And instead of entering that numerically, I will just give it its name in R. That is the third entry in the third row, R3 square brackets 3. So there's my pivotal 1. I now have to subtract that from the first and second rows. And again, I can do that without retyping numbers by just using the third entry in row 1 and the third entry in row 2. I've successfully row reduced the matrix, and while some messy decimal numbers showed up as intermediate steps, it turns out that the solution consists of integers. The top row says x equals 2, second row says y equals 1, third row says z equals 3. Now we're going to look at an equivalent way of doing the same calculation that has important theoretical advantages, one of which will become apparent immediately and one of which will become apparent only in the spring term when we look into the general method for calculating volumes in terms of linear algebra. So I'll start with the same matrix. This time I'll give it the name A. The first thing I have to do is multiply the top row by 1/2, but this time I invent a matrix that does the job. That matrix E1, which is the identity matrix except for having a 0.5 as its first entry, will do the job, and sure enough, E1 matrix multiplied by A has given us our pivotal 1. Now what I have to do is subtract multiples of that top row from the second and third row. Here's a matrix E2 that will subtract 3 times the top row from the second row. I generally have a hard time remembering where the -3 has to go in this matrix, and what helps me is I think I want to modify the second row so it's reasonable for the -3 to appear in the second row, not in the second column. So there's E2 times E1 times A, and I've got 1, 0. I'm halfway toward making the first column pivotal. And E3, which subtracts 1 times the second row from the third row, will give me my first pivotal column, just as before. Nothing is being done differently. The only thing that's being done differently is that I am implementing these row reduction operations by means of elementary matrices. With that in mind, I won't bother reading each one to you. There's another one that divides to make a pivotal entry. Here are a couple more that subtract multiples of the second row from the other 2 rows. At this point, the arithmetic is getting messy, and in the next step, I finally get back to numbers that don't have lots and lots of decimal places in them. And at this point, I have successfully, by multiplying in succession by 6, count 'em, elementary matrices, succeeded in almost completing the row reduction. I have now got 2 complete pivotal columns. I proceed with a matrix E7 that converts the bottom entry in the third column to a 1, and then I use matrices E8 and E9, whose combined effect is to subtract appropriate multiples of the third row from the first and second, with the result that I finally get the completely row-reduced matrix, which I've called AAA, and it's exactly the same as before. Why on earth would anyone want to do this? Well, by multiplying together the 9 elementary matrices that I used, I get a single matrix, let's call it E, that does the row reduction. And the important thing about this matrix E is that since each of the individual matrices that does the row reduction is an invertible matrix, the product of any number of them is an invertible matrix. So I now know that I can always accomplish row reduction by multiplying on the left by some invertible matrix. 99% of the time when you talk about elementary matrices, you don't actually compute the matrices, you merely point out that they exist and that they have a product that's an invertible matrix. In this case, I can use solve to invert that matrix, and in this case, the inverse matrix is just the inverse of A. So we have found a way to invert a matrix by doing row reduction via elementary matrices. But there's no requirement that A has to have an inverse. Whether or not A has an inverse, whether or not it can be row reduced to the identity matrix, this matrix A is guaranteed to be invertible. Well, R makes it a little bit more palatable to do row reduction when you have a large number of equations, but we can automate it still further. In the practical math library is a package function called RREF, which is short for row reduction to epsilon form. This library also contains a function named norm with a capital N that does exactly the same thing as our norm function, but since I had been using the library earlier, I get a warning that I appear to be masking this function. I don't need it anyway, so I don't care. So let's start with our three vectors, display them as a matrix, and try this out. I say RREF of A, kind of like calling your faithful dog, ref A, and presto, the matrix is row reduced, the equations are solved. This function is a little bit flaky, and if you read the documentation, it suggests that it's not for heavy-duty industrial use. It works most of the time. It always seems to work when the equation has a unique solution, but in the case where you have multiple solutions or no solutions, it sometimes gives you an error message, and in that case you have to row reduce by hand. Now, there's nothing about row reduction that in any way relies on the fact that the coefficients in our equations and the constants on the right-hand side are real numbers. In general, linear algebra works in any field. So we can do the same thing for solving equations in a finite field. And that's quite attractive because, as you recall, when you're working in a finite field, there are no fractions. Every non-zero element has an inverse. You can always replace division by multiplication. So we define four functions that do addition, subtraction, multiplication, and division modulo 5. The last one will fail if we try to divide by 0. And I never said I was doing good software engineering in this course. It will fail without giving you an error message. That would be unthinkable if this were a computer science course. So let's start with three equations in four unknowns. What? You say you can't solve three equations in four unknowns? That's not enough equations. Oh, yes, we can. It's just that the solution will not be unique. We're very likely to discover that we have to pick W arbitrarily and then specify X, Y, and Z in terms of it. The process is exactly the same. There's my original matrix, and I want to make the first column into a pivotal column. The first step in that is to divide the first column by 2, but since we're working in Z5, division by 2 is the same as multiplication by 3, which is why the 3 in row 1, column 3 turns into a 4, and why the 4 in the last column turns into a 2. 4 times 3 is 12, but when you divide 12 by 5, the remainder is 2. What do we do next? We have to subtract 3 times the top row from the second row. We have to subtract the top row from the third row. And in doing that, we have cleared the first column. A word of warning about this. I had to put those parentheses in because ordinarily R knows about the order of operations. However, these are special operations that we have decided to define, and it doesn't know that it's always supposed to do multiplication and division before it does addition and subtraction. And those parentheses around the 3 multiplied mod 5 by R1 show do that multiplication before you do the subtraction. Now a situation has arisen that we haven't seen before. We want the pivotal ones to move down and to the right. We're going to get more pivotal ones, but the next pivotal one should be in the second row, not in the third row. So what we do is swap the second row and third row. Now we can convert that 4 into a pivotal 1 by dividing by 4, which is exactly the same thing as multiplying by 4. Subtract 3 times the second row from the first row. We've got our second pivotal column. Divide row 3 by 4 to get a pivotal 1. Now we have our third pivotal column, and we're not going to get any more pivotal columns, are we? You can only have one pivotal 1 in a row, so 3 is the upper limit on pivotal 1s. It's the upper limit on pivotal columns. That means that column 4 has remained as a non-pivotal column, and we are done. How do we solve these equations? Answer: we pick a value for W. Let's pick 3. Interestingly, there are only 5 possible choices. We could choose W to equal 0, 1, 2, 3, or 4. Now I look at the top equation. It says x plus 4W equals 2, and therefore x is going to have to equal 2 minus 4 times W. Similar equations give me y and z, and our final solution is y equals 3, w equals 3. If I take the matrix of coefficients from our original equation and multiply it by that v, we get the right-hand side, 4, 1, 2, our answer checks. Lessons to be learned from this example: everything that works with real numbers works a little bit more neatly with finite fields, and don't worry if you've got lots of unknowns, not many equations. What you will discover is you can pick values of some of the variables arbitrarily. Later in the course we'll be calling those active variables, and the equations determine the other ones, which we'll come to call passive variables. If I use a different value of W, like 1, I carry through exactly the same process, get values of x, y, and z. There is a different, equally good solution to our equation. It checks just fine. And as I mentioned earlier, there are 5 different solutions. If we were working in R, of course, there would be infinitely many different choices for W, and we'd get infinitely many different solutions. In some ways, conceptually, it's much easier to work in finite fields. That concludes my introduction to row reduction.